Lots of the ideas in calculus are geometric in nature and arise as natural consequences of the topology of the real line. Theorems like the intermediate value theorem, the extreme value theorem, and the uniform limit theorem play important roles in the fundamental results of calculus.
For example, the extreme value theorem is pivotal in the proof of the mean value theorem, which in turn lies at the heart of the proof of the fundamental theorem of calculus. As it turns out, these theorems are simple applications of results from topology to the structure of the real line. Topology thus provides a more general framework in which to understand these results, and even lets us apply them to other spaces beyond the real line. The topological property upon which the intermediate value theorem rests is called connectedness. We say that a topological space is connected if there do not exist two non-empty disjoint open sets that cover the space. One consequence of this definition is that the continuous image of a connected set is also connected. This fact actually implies the intermediate value theorem. The statement is as follows. Let f from x to y be a continuous map where x is a connected space and y is an ordered set in the ordered topology. If a and b are 2 points of x, and if r is a point of y lying between f of a and f of b, then there exists a point c of x such that f of c is equal to r.
The intermediate value theorem of calculus is the special case of this theorem that occurs when we take x to be a closed interval in R and y to be R. The proof goes as follows. Assume the hypotheses of the theorem. The sets A equal to f of x intersected with all those elements of y less than r, and b equal to f of x intersected with all the elements greater than r, are disjoint, and they are not empty because one contains f of a and the other contains f of b. Each is open in f of x, being the intersection of an open ray in y with f of x. If there were no point C of x such that f of c is equal to r, then f of x would be the union of the sets A and B. Then A and B would constitute a separation of f of x, contradicting the fact that the image of a connected space under a continuous map is connected.
This demonstrates the concept of the intermediate value theorem in a topological sense. Now we move to the extreme value theorem.
Parte 2. The extreme value theorem in calculus says that if f is a real-valued continuous function on a closed and bounded subset of R, then it achieves its maximum and minimum. In topology, compactness is the property that generalizes the conditions of the extreme value theorem. Compactness is the property that any open cover of the space in question has a finite subcover. In order to generalize the extreme value theorem, we will consider the continuous image of a compact set in a totally ordered set satisfying the least upper bound property.
The real line is an example of such a set, and the extreme value theorem from calculus will immediately follow. For n-dimensional real Euclidean space in the standard metric, we will also show a particularly useful characterization of compactness that does not generalize to other topological spaces.
First, we need a few important facts about compactness. A closed subspace of a compact space is compact. A compact subspace of a Hausdorff space is closed, and the product space of compact spaces is compact. With that, we begin by proving the following. Let X be a simply ordered set having the least upper bound property. In the order topology, each closed interval in X is compact.
Proof, step 1. Given A is less than B, let A be a covering of the closed interval from A to B by sets open in A to B in the subspace topology. We wish to prove the existence of a finite subcollection of A covering A to B.
First, we prove the following. If X is a point of A to B, different from B, then there is a point Y greater than X of A to B, such that the interval X to Y can be covered by at most two elements of A. If x has an immediate successor in x, let y be this immediate successor. Then the closed interval from x to y consists of the 2 points x and y, so that it can be covered by at most 2 elements of A.
If x has no immediate successor in x, choose an element A of A containing x. Because x is not equal to b and A is open, A contains an interval of the form x to c for some c in A to b. Choose a point y in x to c, then the interval x to y is covered by the single element A of A.
Let C be the set of all points y greater than A of the closed interval from A to B, such that the interval from A to y can be covered by finitely many elements of A. Applying step 1 to the case where x is equal to A, we see that there exists at least one such y, so C is not empty. Let C be the least upper bound of the set C. Then A is less than C, which is less than or equal to B.
We show that C belongs to C. That is, we show the interval A to C can be covered by finitely many elements of A. Choose an element A of A containing C, since A is open. It contains an interval of the form D to C for some D in A to B. If C is not in C, there must be a point Z of C lying in the interval D to C, because otherwise D would be a small upper bound on C than C. Since Z is in C, the interval A to Z can be covered by finitely many, say n, elements of A. Now Z to C lies in the single element A of A, hence A of C is equal to A of Z union Z of C, can be covered by n plus 1 elements of A. Thus, C is in C, contrary to assumption.
Finally, we show that C is equal to B, and our theorem is proved. Suppose that C is less than B. Applying step 1 to the case, where x is equal to C, we conclude that there exists a point y greater than C of A to B, such that the interval from C to y can be covered by finitely many elements of A. We proved in step 3 that C is in C, so the closed interval from A to C can be covered by finitely many elements of A. Therefore, the interval A to Y, which is equal to the interval from A to C in union with the interval from C to Y, can also be covered by finitely many elements of A. This means that Y is in C, contradicting the fact that C is an upper bound on C. We are now ready to tackle the extreme value theorem. Let f from x to y be continuous, where y is an ordered set in the ordered topology. If x is compact, then there exist points c and d in x such that f of c is less than or equal to f of x, which is less than or equal to f of d for every x in x. The extreme value theorem of calculus is a special case of this theorem.
Proof. Since f is continuous and x is compact, the set A equal to f of x is compact. We show that A has a largest element m and a smallest element m. Then, since m and m belong to A, we must have m equal to f of c and m equal to f of d for some points c and d of x. If A has no largest element, then this collection of open rays forms an open covering of A.
Since A is compact, some finite subcollection covers A. If A sub I is the largest of the elements A1 to AN, then A sub I belongs to none of these sets, contrary to the fact that they cover A. A similar argument shows that A has a smallest element.
The uniform limit theorem. Finally, although this last theorem is more obscure and not as popular as the other two, it provides a useful characterization of the conditions under which things like power series or other sequences of functions can converge to a continuous limit.
The most obvious way of defining the limit of a sequence of functions is pointwise. The value of the limit function at x, if it is defined, is the limit of the sequence of function values at x. This is most commonly referred to as pointwise convergence. Unfortunately, though, this definition of convergence of functions is not adequate to guarantee that the limit of a sequence of continuous functions is continuous. For example, this sequence of functions on the closed interval from 0 to 1 defines a sequence of continuous functions that converges pointwise to this discontinuous function. To fix this, we define a new notion of convergence, uniform convergence. We say that a sequence of functions f sub n from a topological space x into a metric space y converges uniformly to a function f from x to y if, for every positive real number epsilon, there exists a natural number n such that for any n greater than or equal to n, the distance between f sub n of x and f of x is less than epsilon for all x in.
As it turns out, this is enough to guarantee the theorem that we want. The uniform limit of continuous functions is continuous. If it exists, let f sub n from x to y be a sequence of continuous functions from the topological space x to the metric space y. If f sub n converges uniformly to f, then f is continuous.
Proof. Let V be open in Y. Let x naught be a point of the preimage of V. We wish to find a neighborhood U of x naught such that f of U is a subset of V. Let y naught be equal to f of x naught. First choose epsilon so that the epsilon ball about y naught in the metric on y is contained in V. Then, using uniform convergence, choose a natural number n so that for all little n greater than or equal to n and all x in x, the distance between f sub n of x and f of x is less than epsilon over 3. Finally, using continuity of f sub big N, choose a neighborhood U of x naught such that f sub n carries U into the epsilon over 3 ball in Y centered at f sub n of x naught. We claim that f carries U into this ball of radius epsilon about y naught and hence into V as desired. For this purpose, note that if x is in U, then the distance between f of x and f sub n of x is less than epsilon over 3. The distance between f sub n of x and f sub n of x naught is less than epsilon over 3. And the distance between f sub n of x naught and f sub x naught is less than epsilon over 3. Adding and using the triangle inequality, we see that the distance between f of x and f of x naught is less than epsilon as desired.